Good evening, everyone. Thanks for joining us this evening. My name is Melanie Wooden, and I have the pleasure of serving as the Dean of the Faculty of Arts and Science here at the University of Toronto. Before we begin, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Welcome to the 2025 Martin Lecture in Physics. The Martin Lecture was created in honor of the Martin family and their exceptional generosity to the Faculty of Arts and Science and the University of Toronto. I can think of no other family with deeper or more broad ties to the University of Toronto. Since the late 1800s, some 60 members of the extended Martin family have studied here, including each of Mary and Ron Martin's 4 children and 6 grandchildren. I'm absolutely delighted to see many members of the Martin family here today, including alumna. And also wonderful to see Professor Peter Martin here, my colleague from the professor in the Canadian Institute for Theoretical Astrophysics, and grateful for his formal and informal leadership of that for so long. The Mary and Ronald Martin Graduate Scholarships were established through a generous bequest of Mary and Ron Martin, who were staunch believers in the power of education. And for that, we are incredibly grateful. What a truly inspiring family in so many regards. The scholarships that they established help us attract the most promising graduate students from across Canada and across the world. They are awarded each year to the top graduate students in 4 disciplines: physics, astronomy and astrophysics, ecology and evolutionary biology, and public policy, the professional specialties of Mary and Ron's 4 children. Accordingly, the annual Martin Lecture rotates in focus of these 4 departments each year, where we strive to bring compelling talks that explore the most relevant and fascinating issues of today. And tonight is certainly no exception, as we are joined by Nobel Laureate Geoffrey Hinton. As you all know, Professor Hinton was recently awarded the Nobel Prize based in part on his training of artificial neural networks using physics. So tonight, we are in for a real treat. And tonight's reflections on the early days of artificial intelligence will inspire new questions and ideas that will pave the way for future discoveries that we can only begin to glimpse. So it's my pleasure now to turn the podium over to my colleague, Professor Paul Kushner, the chair of the Department of Physics, to introduce our speaker. Over to you, Paul.
Thank you, Dean Wooden. It is indeed an honor to introduce tonight's keynote speaker, University Professor Emeritus Geoffrey Hinton. Dr. Hinton's prolific pursuit of ideas across artificial intelligence and cognitive science have led to an incredible array of recognitions, including fellowship in the UK Royal Society and Canada's Royal Society, recognition as a member of the Order of Canada, and the ACM Turing Award. But tonight's Martin Lecture is a perfect opportunity to celebrate and explore the fascinating connection of Professor Hinton's work to the discipline of physics in the setting of his being awarded the top honor in our field, the 2024 Nobel Prize. He received this honor along with Dr. John Hopfield for using statistical physics as a tool of cognitive science. Dr. Hinton and colleagues used statistical physics to discover that the many parts of an artificial neural network, systematically organized and connected, could be used to recognize and recreate patterns in data sets. This, together with framing ideas from neuroscience, from chemistry, and major advances of mathematics, engineering, and computer science, led to today's revolution in artificial intelligence. Today, at the leading edge, modern statistical physics used in analysis of subatomic and atomic physical systems, novel materials, and myriad biological, chemical, and environmental systems is leading to a deeper understanding of AI itself, and thus feeding further advances in AI. As Professor Wooden has pointed out, our research environment in physics at the University of Toronto is in a great position to discover more about the many connections between statistical physics and AI. With this in mind, we look forward to Professor Hinton telling us about the intersections of physics with machine learning. Now, before he gets started, I would like to recognize Dr. Hinton's achievements on behalf of the entire Department of Physics in our own very small way by offering him an honorary appointment to our graduate faculty in the Department of Physics. Pretty good stuff, right? So Dr. Hinton has graciously accepted this appointment, which we've guaranteed comes with absolutely no administrative duties. Also, we have a cute frame as well to show him. Also, after his lecture, I'll be inviting Dr. Jonathan Yoni Khan, our new colleague in the Department of Physics, to host a fireside chat. So you have to imagine the cheery fire over there, with Professor Hinton, and they'll be further exploring the connection between Boltzmann Machines, physics, and AI. I'll spend a moment introducing Professor Khan after Dr. Hinton's keynote. So with this, I'd like you all to join me in welcoming this year's Martin Lecturer in Physics, Geoffrey Hinton.
So I should say I was once offered a cross appointment in statistics, and I declined it on the grounds that I don't know any statistics. If I was consistent, I would decline this one too, but I'm not. So back in the 1980s, I worked on two different learning procedures. And there's something slightly embarrassing about these two procedures. One of them was very interesting, and the other one worked. So I'm going to start off by talking about the one that worked, which was just a dumb application of the chain rule of differentiation. And I'm going to talk about that for about 20 minutes or so, because that actually worked. And that underlies current AI, current deep learning in AI. And I'll talk about a couple of the things we did there. I feel I need to do that to be sort of honest about what actually worked. Then I'll talk about the other learning procedure, which is much more interesting and uses statistical physics and didn't actually work very well. But it's very interesting. Okay, so here goes. So in the history of AI, there were two approaches going back to the 1950s. There was the logic-inspired approach, where the idea was, no, I can't see the slides, okay. Where the idea was that the essence of intelligence is reasoning, and we need to study how reasoning works, and reasoning is done by manipulating symbolic expressions. The other approach was neural nets, where the idea was the essence of intelligence is learning connection strengths in neural nets, and don't worry about reasoning until you figure out how the brain learns. And Turing and von Neumann both believed in the second approach, but they both died young, and so the first approach dominated for 50 years. I'm going to very quickly explain what a neural network is in case there's people here who don't know what they are. You have layers of neurons, which are relatively simple devices in this work. Real neurons are very complicated, but we make gross simplifications. So in that sense, I'm a physicist. I sort of ignore all the details. Physicists like horses to be spherical. And you have multiple layers of these things. You have connections between neurons, and you want to learn the connection strengths, so when you put something in, the right thing comes out. And typically what you put in is the pixels of an image, and you'd like to come out the category of the object in the image, a label for the image. So everybody can understand that you could learn a neural network in the following way. Pick one of the connection strengths, and change it a little bit, and see if the whole thing works better or worse. That's the sort of mutation method. And that'll definitely work, and it'll take a huge amount of time, because nowadays neural networks have 1 trillion weights. So you'd have to, 1 trillion different times, pick one of the weights, change it a little bit, see if things work better. And to see if things work better, you need to give it lots of examples, because it might make it work better for some examples and worse for other examples. So it's hopelessly slow. Backpropagation is essentially just doing the same thing, but figuring out for all the weights in parallel whether increasing them a little bit or decreasing them a little bit will improve the performance. So in backpropagation, you send a signal forwards through the network, you look at the difference between what you got and what you wanted, and then you send a signal backwards. And by doing this and using the chain rule for differentiation, you can figure out for every connection at the same time whether you should increase it or decrease it a little bit. And that's what you do. And amazingly, to a lot of people's surprise, that works really well. It works really well if you've got a lot of data and a very fast computer. So in 2012, 2 students in my lab, Ilya Sutskever, who you may have heard of, he just started a company that's producing nothing and is now worth $30 billion. I suggest the dean might like to contact him. Ilya Sutskever and Alex Krzyzewski, who was an amazing programmer, they made a system that could recognize objects and images much better than standard computer vision. It got nearly half the error rate of standard computer vision. And that kind of opened the floodgates for neural networks. People were using them already, particularly in speech, but the performance of this network made it clear that they really do work, and they really do work on real images. And everybody in computer vision over the next year or so switched to using neural networks. A couple of years before that, papers on neural networks were just routinely rejected by computer vision conferences because everybody knew this stuff was nonsense. And then a few years later, nearly all the papers were about neural networks. So that made a big impact. And at least it was done by students in my lab, so I'll get a lot of credit for that. In fact, I was asked by the Computer Museum, which now has a display of the AlexNet. I was asked by the Computer Museum if I could provide a quote for them. And so the quote that I agreed with Alex and Ilya was, it was Ilya's idea to do it, Alex made it work, and I got the Nobel Prize. Okay, but what about language? So many people in symbolic AI said this stuff will never work for language. That's quite different. And if you look on my webpage, you can find quotes from them saying how this will never work for language. You can also find GPT-4 explaining to these people what was wrong with their quotes, which is fun. There was a linguist called Chomsky, who you may have heard of. And he's a sort of cult figure. He managed to convince people that language isn't learned. And it's pretty obvious that language is learned. In the same way it's obvious that Obama had a bigger crowd. But if you can convince people the language isn't learned, then you've got them. And several generations of linguists are convinced that language is not learned. And Chomsky never had a theory of meaning. He had a theory, his theories are all about syntax. He, of course, thinks all this stuff is complete nonsense, even though it can have a pretty good argument with him now. But he still thinks it's complete nonsense. It's not really understanding anything. So the linguists thought the idea of big neural network just using data to learn syntax and semantics was completely ridiculous. It would never work. And for many years, it did never work. But eventually, with big networks, it worked very well. And that's what you see in these large language models now. And I want to talk a little bit about the origin of these large language models and what meaning is. So there's 2 very different theories of the meaning of a word. One theory is that the meaning of a word depends on how it relates to other words. So you have a bunch of sentences with multiple words in. How it's distributed with other words determines its meaning. That's a theory that comes from de Saussure more than 100 years ago. And that's what the symbolic AI people basically believe. And to capture meaning, you probably need something like a relational graph. The other theory comes from psychologists, and it's that the meaning of a word is a big bunch of features. So Tuesday has some huge bunch of features, and Wednesday has some huge bunch of features, and they're quite similar bunches of features. Now, those 2 theories sound very different, but in 1985, in order to convince people that backpropagation actually worked, I developed a system, a tiny language model, that unified those 2 theories. So the idea is that you're going to use features of words to predict the features of the next word in a string of words, and from the features of the next word, you'll predict the word. But the only thing stored within your system will be how to convert a word into features, and how the features of words in a context should interact to predict the features of the next word. You don't actually store any strings of words. So the symbolic AI people thought you store strings of words in your head, or strings of symbols, and you manipulate those with rules to get other strings of symbols, just like in logic. This is a completely different idea of what meaning is. You convert a word into a bunch of features. You know how features interact with features of other words to predict features of the next word. And what meaning is taking a string of words and converting those words into the appropriate features. And that may be difficult. You might have a word like May, which could be a month or a woman's name or a modal, and you have to use interactions with neighboring words to decide what features to use for May. But essentially, the large language models that you have now, the way they work is they take words, actually fragments of words, and they convert those into vectors of features. They then have many layers of refining those vectors of features by doing interacting to disambiguate things. And then they predict the features of the next word, and from those features they can predict the next word. And so they work just like the small language model, except they're much bigger, and the way the features interact is much more sophisticated. So I'm going to show you, because it's something I did, the tiny language model from years ago, because that's very easy to understand. The big language models, it's hard to understand how they're representing knowledge. The tiny language model, it's easy to see how it's representing knowledge. So I took some relational knowledge, 2 family trees, and you can convert the information in those family trees into 3-word strings, so triples of words. If you use relationships like son, daughter, nephew, niece, and so on, you can have 3-word strings like Colin has father, James. And from those strings, if you learn some of the strings, you can now predict other strings. That's called generalization. The way people in logic would do it is they would say, you have to have rules that look like this. So you have to have a rule that says if X has mother Y and Y has husband Z, then X has father Z. Or the other way around. And they thought what you should do is search for those rules. Now, that's fine if there's discrete rules and things are always very certain. As soon as you have some exceptions and some uncertainty in the data and errors in the data, searching for discrete rules is much harder. And the idea was we get a neural network to find those same rules, but by searching a continuous space. There's an interesting thing about continuous and discrete in computer science. For a long time, computer scientists defined themselves as, we're not interested in real numbers, we're only interested in discrete things like graphs, because we're real computer scientists. And then the mathematicians explained to them that actually, even if you want to do discrete things, using real numbers, using big matrices to understand discrete structures is a good idea. So the point about neural networks is they use real numbers and they search in that space, and searches are much easier in that space. So I used a network like this. It has 2 inputs, a person and a relationship. It converts those into features, actually only 6 features for each of them, because it was a tiny computer that goes billions of times slower than the computers we have now. This was in 1985. And then it takes the features of the words, they interact, they predict the features of the next word, and the whole thing is trained by simply back-propagating from the output, the error in the output. You send a signal backwards, and it tells you how to change the connection strengths that turn symbols into feature vectors, and make those feature vectors interact. And it learned interesting features that made sense, so you could see how it worked. So, for example, for people, if you think about those 2 family trees, these were 1950s family trees. There was no divorce, there was no adoption, nothing funny, just very, very straight American families from the 1950s. And so, for example, Italian people would only marry Italian people. And so if you know the nationality of the input person, you know the nationality of the answer. So it's a very good idea when you convert a symbol into features to have nationality be one of the features. It's not explicit in the training data, but it's a strong regularity that Italians only marry Italians. So it learns the nationality feature. It also learns features like generation. And for relationships, it learns features like the answer should be 1 generation up from the input. So if you're looking for somebody's uncle, that should be 1 generation up from them. And because for relationships it knows things about some relationships require you to be 1 generation up, and because it's learned to extract the generation of the input person, it can then predict the generation of the output person. And so the way it gets to the correct output person is by predicting a bunch of features of the output person, like their nationality and their generation, and which branch of the family tree they're in, and from that it can predict the output person. So it actually worked. It didn't have much impact at the time. I thought this was terrific because I've managed to unify the psychologist theory of meaning, which is a big bunch of features, with the sort of structuralist theory of meaning, by getting the features to produce the sequences, and by using sequences to learn the features. So you could go from sequences to features and from features back to sequences. But the symbolic AI people weren't very interested. But over time, people got more and more interested. And I did get a review that I'm still annoyed about. Every scientist has some review they're really annoyed about. I got a review in 2007 that said, I was talking about turning words into features and having the features interact. And the review said something like, Hinton has been doing this stuff for many years and nobody's interested. It's time to move on. That was 2007 when it was already beginning to work. Okay, and I'm going to finish this stuff about backpropagation by trying to give you an analogy of how meaning works, how words work to give you meaning. So what Chomsky didn't really understand is you have to have models of things. And words are a particular way of building models. They're actually a much better way of building models than anything statisticians have, because you can make very sophisticated models with them. So think of it like this. Suppose you want to know where stuff is in 3D. Like you want to model the shape of a Porsche, and you're not too worried about aerodynamics, so you don't care about the surface. You can make it out of Lego blocks, and you can approximate it pretty well out of Lego blocks. Well, words are like Lego blocks, except for some differences. The first difference is we have, say, 30,000 different types of Lego block. That's one difference. The second difference is they're not rigid. They can move about a bit. If I tell you the name of a word, it defines a shape, but the shape has some flexibility to it. It might, of course, define several alternative shapes, but it's not infinitely variable. I mean, infinitely malleable. The word defines a rough shape. The words then interact with each other to determine the shapes of the individual words. And you can think of that as the words need to fit together somehow. Now, with Lego blocks, you have a little plastic cylinder that goes into a little cylindrical hole, and they snap together. The way you do it with words is every word has a whole bunch of hands on it. And as you change the shape of the word, you change the shape of those hands. And words have to shake hands with other words. They have to decide which other words to shake hands with. And they shake hands with other words whose hand shapes match their hand shapes. So think of getting the meaning of a sentence as you have these words which have these somewhat flexible shapes, and as you change their shapes, their hands that they shake hands with all change shape. And what you have to do is find out how to deform them so they can lock together nicely. And when you do that, when you deform these shapes and they lock together nicely, that is the meaning. It's a way of modeling things, and that is what a meaning is. There's just one other difference, which is that these words are like 1,000-dimensional instead of 3-dimensional, but we're not going to make a big deal out of that. 1,000-dimensional spaces, the way you think about them is you think of a 3-dimensional space and just say 1,000. I think that must be what physicists do too, but I don't know. Maybe 4-dimensional spaces they can imagine, but when you get up to 11 dimensions, I don't think they can imagine it. Okay, that's it for the first part of the talk. I talked a little bit about backpropagation. I talked about two of the things we did on backpropagation, a tiny language model and recognizing objects in images. And those were both very influential in the development of the use of backpropagation. And that's what led to, they were very influential pieces of work that led to the neural nets we have today, the deep neural nets that do everything. Now, an unfortunate thing about backpropagation is it's hard to see how you could do it in a brain. And I was always interested in how the brain might actually be doing it. That was one of the points of doing this. So if you ask, what's backpropagation like as a model of how the brain learns? Well, nobody's found a good way to implement backpropagation in something neurally plausible. We can do it for little systems, but as soon as you take a big system, we can't implement in brain-like stuff anything that works as well as backpropagation. The cortical neurons send binary signals to each other. They don't send real values like we do in backpropagation. The backward paths of backpropagation, so you put in an image, you go forwards, you recognize something. If you know what it is that's there, you can send an error signal backwards, but you have to know what's there, and that's already a problem. And when you send this signal backwards, you're interfering with the pipeline of perception. We do perception in real time, and stuff is always coming in. You don't want to have to stop and send stuff back. So that's another problem. A problem that's new, because only in the last few years have we known this, backpropagation works much better than the brain. And that's the reason for thinking it might not be how the brain does things. It works much better than the brain in packing a lot of information into a few connections. So these big language models have about 1 trillion connections, the biggest ones, and your brain has about 100 trillion connections. Let's suppose 10 trillion of those are used for knowledge, which seems not unreasonable. We're physicists, so we just do things in orders of magnitude. So at least 1/10 of them are going to be used for knowing stuff. And things like GPT-4 know thousands of times more than any one person. They're like a not very good expert at everything. So backpropagation is actually much better at squeezing a lot of information into connections than whatever it is we got in the brain. Perhaps because the brain's solving a very different problem. Our problem is we've got lots of connections, like 100 trillion, but we don't live very long. We only live for about 2 billion seconds. Luckily, it's a little bit more than 2 billion, but about 2 billion. So we don't get much experience, but we've got a lot of connections. In these big language models, they have huge amounts of experience and not many connections. So backpropagation is good if you have a lot of data and not many connections. Whatever it is our brain doing is good if you have a lot of connections and not much data. And it's optimized for that, presumably. So this leads to the question, is there maybe a completely different way to get the gradient? A way of getting the gradient of how you should change your weight to make the system work better, that is the gradient of the error the system makes with respect to the weight, that's just totally different from backpropagation. And that means you don't have to keep interrupting pipelines and things. And it turns out there is. And that's where statistical physics comes in. Because I'm going to use a bit of magic from statistical physics and show you that there's a very simple learning procedure, which is actually very like a procedure recommended by the great Canadian psychologist Donald Hebb in around 1949, where he said neurons that wire together, fire together, wire together. So his learning algorithm was, if two neurons are active together, increase the strength of their connection, roughly speaking. That doesn't work. If you just do that, connections only get stronger. He didn't say how connections get weaker. And the answer is you have to do something else as well, and then that algorithm works. So I'm going to start off by explaining things called Hopfield nets. Hopfield nets, as you might imagine, were developed by John Hopfield. And they use binary neurons. So rather than having real values now, we're going to have binary neurons that are either on or off. Hopfield actually used 1 and -1, but I'll talk as if he used 1 and 0. And that fits in with cortical neurons, which in a short period of time either send a spike or don't. Okay, so we've got these binary neurons. And we're going to have symmetric weights between them, which is completely unrealistic, but we're physicists, so that's okay. So what symmetric weights means is that if, take those two neurons on the top there, when the one on the left fires, it sends an input of -5 to the one on the right, and similarly when the one on the right fires, it sends an input of -5 to the one on the left. And so we have weighted connections. The weights are always symmetric in a Hopfield net. And I'll call the global state of the network, that is an assignment of 1s and 0s to all the neurons in the network, saying whether they're firing or not firing. I'll call that a configuration. And configurations have energies. If you want to get rid of a few minus signs, we'll talk about configurations having goodnesses. And the goodness of a configuration is simply, for all pairs of active neurons, just add up the weights on the connections. So for the 3 neurons that are active there that have 1s, you add up the weights, you get 4. So the energy is -4, the goodness is 4. That same network has a different, and that's a local minimum. You can't change any neurons without raising the energy or lowering the goodness. But there's a different state of that network, which has greater goodness or lower energy, which is, okay, I already said all that, which is if you take this same network and you turn on those 3 units, then the energy of that state is -5, the goodness is 5. It's a better minimum. So the point is to show that even in a tiny net like this, you can have 2 different minima. Now, Hopfield realized that means you can use these minima as memories. So his model of what you're going to do with a net like this is you're going to use it to store memories. And then you're going to get a content addressable memory. If I give you a little bit of a memory, you can fill in the rest by letting this network settle down. Oops. Sorry, I clicked twice. Yes, you can access a memory just from knowing part of the memory. Now, back when he did that in the early 80s, that was before Google, and content addressable memory was something that seemed quite magical. As soon as Google came along and made big inverted indices, it was easy to do content addressable memory, and we're all used to that now. But this was a way of doing content addressable memory in a neural network. So Terry Sinofsky and I went to a talk by Hopfield, and we figured out you could use Hopfield networks for something completely different. You could use Hopfield networks for doing perceptual inference, for looking at an image and interpreting what's in the image. And so the idea is to have 2 sets of neurons. We'll have input neurons, where you represent what's in the image. I'll call those the visible neurons. And you have hidden neurons that represent an interpretation of what's in the image. And you'd like the energy of the whole system to represent the badness of the interpretation. So by finding low energy states of this whole network, you're finding good interpretations. And so if you show it an image, what you're doing is you're fixing the states of the visible units. Let's suppose it's a binary image. So you fix the states of the visible units to represent some binary image. And then you'd like the network to settle down by repeatedly going around updating the states of units to make them go to lower energy states. And you'd like to find a good interpretation of that input. And so that raises a couple of problems. Oh, here's an example. I might give you an ambiguous line drawing, and I've sort of illustrated 2 possible interpretations of the Necker cube, one in which it's at a different orientation from the other one. And so the very same input image can have 2 very different interpretations, which are more or less equally good. The one on the left's a bit better, because it can sit nicely on the surface in the way the other one has to be glued to the ceiling. But apart from that, they're more or less equally good. And your brain can see both of those. And so this is a nice example of a system that has 2 different interpretations of the same image. And it seems nice to model that by 2 different energy minima of the same system. So how could we make a system that can come up with those interpretations of an image like that? Well, first of all, we have to think about the image is going to be made of lines. We're just going to use images with straight lines. And we have to think about what a straight line depicts out there in the world. So I want you to imagine that out there in the world, you have an edge of an object, and then you have a window between you and the object, and using a marker pen, you draw that edge on the window. So you can see there, yeah, the laser doesn't work, I don't think. You can see there that I've drawn an edge on the window, and there's 2 lines of sight go through the ends of the edge, of the line that I've drawn on the window. And there's many different edges that could have given rise to that line. So that edge, because the 2 lines of sight go through the ends of it, would have given you that line in the image. But so would this edge, or this edge, or this edge. And you can see there's a whole family of edges will give you the same line in the image. So you've lost information. And the point about visual perception is you want to get back that information. And to do that, you need to use some assumptions. So to build this into a neural net, we know just from optics that you can only see one of those edges at a time. And so we know that line in the image is going to be one of those edges, but we don't know which one. So we can wire up a network by saying, let's suppose we have neurons that represent 2D lines, And we'll activate a few of those to represent the lines in the image. And we know that for each of those lines, only one of the possible edges is present. So what we'll do is we'll have all the edges that might have given rise to that line, and the line will try and activate all the edges. Those are the green connections. But also, all those edges will fight one another, because those are all edges that couldn't be seen at the same time. They get in each other's way. So what we really know when we see that line in the image is one of those edges is present, but we don't know which one. And our neural network will try and capture that by saying the line excites all those edges and the edges all inhibit each other. The inhibition is very important. The same for the another edge in the image, like that. And so that's got sort of optics into it. But now let's get some assumptions into it. So here's a test I sometimes do to distinguish computer scientists from physicists. If you give a physicist the following problem, x plus y equals 384, what are x and y? The physicist will think you don't know much about equations, and you can't possibly answer that question. And the computer scientist will tell you x and y are 256 and 128, but he doesn't know which is x and which is y. And that's because in a computer scientist world, you're dealing with powers of 2 all the time, just because of the way computers work. And so they're very familiar with numbers like 384, and they know when you see 384, it's probably 128 plus 256. Particularly if you program NVIDIA GPUs. So we're going to use the same trick here. We're going to say, knowing what 3D edge is represented by a line in the image is basically impossible, but you can use assumptions about the way the world normally is, and that can help you a lot to come up with a sensible interpretation. So what we're going to do is we're going to say that if you see two lines in the image that join in the image, they probably join in depth in the world. They don't have to. From my point of view, I could have two lines sort of like this, where my eye just happens to line up, so they appear to join, but they don't actually join. But I'd have to be at a very special viewpoint for that. So it's a very good assumption that if you see two lines join in an image, they correspond to edges that actually join in depth at that point. So we can take edges that join in depth, 3D edges that correspond to different lines, but join in depth at the point where the lines join, and we can say they should support each other, because they join in depth. Now, if they join in depth at a right angle, we can say they should support each other a whole lot, because in this little world we're in, we tend to see right angles much more often than other things. That's actually a very bad piece of psychology, but it will be a whole nother lecture to say why it's not true that we prefer right angles. What we actually prefer is edges that line up with the rectangular coordinate system we've imposed on an object. And if you impose a rectangular coordinate system that doesn't line up with two edges, if two edges like this, and your rectangular coordinate system's like that, you have no idea whether this is a right angle. You're only interested in lining up with a coordinate frame. You're not really interested in right angles. But anyway, I had to put that in because I don't want to say false psychology. So now we've got all the things we need for doing interpretation. We have the 2D lines. Those are our inputs here. Those are our visible neurons. We know what edges each 2D line might be. We know how edges should fit together most plausibly. And so all we've got to do now is solve a search problem. What we want to do is take the states of the visible neurons and search for a low energy state configuration of the system. But we have a problem. We might get trapped in a local minimum. And can we do better than just going downhill in energy, updating the neurons so you go downhill in energy and ending up in a local minimum? And it turns out you can do quite a lot better than that. And you do better than that by using noisy neurons. And it turns out if you use noisy neurons for doing search, then a piece of magic happens and you get a very simple learning procedure. But I'll come to that. So, in a Hopfield net, the energy is actually the energy of configurations of binary things, which are really the corners of a hypercube, but I'll draw it as if it was some one-dimensional thing. So imagine a landscape, and the state of the network is a little ball on the landscape. And as you change the states of neurons, you're moving about on that landscape. And the update rule for Hopfield net says, go to whichever state lowers the energy. And if you get trapped in a local minima, you then can't, you're stuck. And you can't get into a deeper minimum like B. And the Hopfield update rule says, if the total input to a neuron is positive, turn it on. And if it's negative, turn it off. So it's that square function at the top. But suppose that we make the neurons noisy. Suppose we introduce jitter in the decision rule, or what a physicist would call temperature. Then we can have a decision rule set that says that sometimes when it gets total negative input, you turn it on. And sometimes when it gets total positive input, you don't turn it on. Obviously, generally when it's got positive input, you turn it on. But if it's only small positive input, maybe you only turn it on a little more than half the time. So that's that decision rule. And notice that that graph is showing you the probability of the neuron turning on. These neurons are still binary neurons. They don't have real values. But their probability of turning on is governed by a decision rule like that. Now, if you use neurons like that, then they can jump to higher energy states. So this ball bearing on this energy surface can jump over that barrier and get to the lower energy state. Now, it might also jump back, but it's less likely to jump back because the energy barrier is higher from that side. So, the way we're going to interpret a binary image is we're going to clamp the binary image on the visible units, and then we're going to go around updating neurons using this probabilistic decision rule. For a physicist, we're going to use a temperature of 1. And we're going to pick a hidden neuron, we're going to compute the total input it gets, and then we're going to stochastically decide whether to turn it on or off, probably turning it on if it's positive input, but occasionally turning it off. And we just keep doing that with the hidden neurons. And that will do better than just going downhill. That'll typically get us to one of the deeper energy minima. Now, if we do that for long enough, we'll reach a state called thermal equilibrium. And if you're not a physicist, you think thermal equilibrium means things have settled to some particular state. But it doesn't mean that at all. It's what a statistician would call a stationary distribution. It means that even though the neurons are changing states, the probability of finding the whole system in a particular state has stabilized. And the best way to think about it is imagine like a gazillion neural networks that are all identical. They all have identical inputs. And we start them all off in the same state, let's say. But then each neural network makes its own stochastic decisions about how to turn on or turn off hidden units. And you can imagine if you took all possible binary states of the network, when we start off, they all start off in the same state. So if you did a histogram of how much these different binary states are occupied, all the systems would be in the first state and none would be in any other state. But then you keep running this decision rule, and gradually what happens is systems adopt other configurations. And after you run it for a while, you'll have a histogram where low energy configurations have lots of systems, and higher energy configurations have less systems, and very high energy configurations have very few systems. And even though any one system will jump between configurations, the histogram will stay fixed if you have enough systems. That's what thermal equilibrium is. It's when the histogram stays fixed, even though individual systems are jumping all over the place. And the nice thing about that fixed histogram is it has a very nice property, which is that the probability, the number of systems, or the probability of being in a particular configuration, only depends on the energy of that configuration relative to the energy of other configurations. It doesn't depend at all on the history. You have to run it long enough so it's forgotten where it started. And then you get this nice guarantee that the probability of being in a state, a configuration, just depends on the energy of that configuration relative to the energy of all the other configurations. So, we'll come back to how you use that for learning in a minute, because that's the neat thing about Boltzmann machines. For now, let's go back to this line drawing. What we'd like to do is we'd like to not have to hand wire this thing. We'd like it to learn all those connection strings. So we'd like to just give it some visible units where it represents the line drawing, and we'd like to just give it a pool of hidden units with random connections and have it learn all that structure. Now, it won't actually learn that structure. I put that structure in because it's easy to understand that a system like that might work. It'll learn a much more sophisticated structure, but it'll do the same job. It'll be able to interpret line drawings. And so the question is, how could you learn all that structure just by looking at a lot of line drawings? And it seems very implausible that you could do that. And it particularly seems very implausible that you could learn, for example, we have to learn the weights between hidden units. That connection that says join in 3D, it has to learn all those connections. And it's not at all obvious how you would learn all those just by looking at data. And it turns out there's a very, very simple learning rule. So I already explained thermal equilibrium. Yeah, that's what I already explained because I got ahead of myself because I couldn't see the slides. Now let's think about, we've got a system, we've already got the weights in, suppose I put them in by hand, and instead of getting it to interpret a binary image by picking the states for the hidden units that represent the 3D edges, I'm going to get it to do something else. I'm going to get it to generate a binary image, generate a line drawing, an image of lines. And the way I'm going to do that is I'm going to start off the whole system in some random state, and then I'm going to go around picking neurons at random and updating them, and just keep doing that. And after a while, I'll reach thermal equilibrium. And then I'll look to see what the line neurons are doing. And so we could think of an objective in learning weights. We could say, if you show me a whole bunch of line drawings of rectangular objects, my objective is to find weights so that if I start the network off in some random state and just go around updating units one at a time, when I look at the hidden unit, when I look at the visible units, after it's reached thermal equilibrium, they will look like one of these line drawings I showed it. It'll have, in other words, it'll have a model of what line drawings look like. Because if I put it in a random state and say, settle to something you find plausible, it'll come up with a line drawing. And of course, finding plausible for this network means a low energy state. The lower the energy, the more plausible things are for the network. So, we have a way of, if we have the right weights in the network, we have a way of generating data. We also have a way of interpreting data. To generate data, you update all the units and just look to see what the visible units are doing. To interpret data, you fix the visible units and then go around updating the hidden units and look to see the interpretation in the hidden units. Right, so that's generating. And I already said this. The aim of the learning is when the network's generating, you'd like it to produce stuff that looks like the real stuff. So you can think of generating in this network as dreaming. And in fact, Francis Crick postulated that when you dream, what's happening is you're getting your neural network to generate stuff. He also postulated that you're getting it to generate stuff in order to get rid of that stuff. As you'll see, this learning rule exactly fits his speculation. The idea of learning this way, the idea of learning a generative model that will generate images like the ones you see, the purpose of that may not be to generate images. You do generation during the learning, but your real purpose may be to get at these hidden variables that explain what's going on in the image. Because if you're doing perception, you're much more interested in not the 2D lines in the image, but the 3D edges in the world. So the point of doing this generation is so you can do learning, and the point of learning is to get at these variables that are not in the input, but are things you made up that explain the input. Okay. So here's our outrageously optimistic approach, which actually works very well in theory and not so well in practice. You start with a neural net that has lots of hidden neurons with just random weights between them, and you have some data, which is the states of the visible neurons, and you keep showing it these line drawings, these images, and you want the network to learn for itself all that hidden structure that will interpret images. And you'd like to do that with a nice simple learning rule. And so This is where statistical physics meets neural nets, and there's just a beautiful synergy there. We're going to have two phases. We're going to call them a wake phase and a sleep phase. And in the wake phase, what you do is you put an image in, and you go around updating the hidden units till you settle to thermal equilibrium, and then use the Hebb rule. For every pair of units, every pair of connected units that are on at the same time, both on, increase the connection strength a little bit. That's exactly the rule Donald Hebb proposed. I'm ignoring the temporal aspects of it, but things that fire together, wire together. That's all you do. It's a very simple rule. There's nothing like backpropagation going on. And then for the sleep phase, you don't give it input. You turn off the input and you get it just to generate. So it's now generating images. And every time two units are on together, you decrease the strength of the connection. It's an anti-Hebb learning rule. And that's it. And what's amazing is those two simple rules go around updating hidden units when you're giving it input and increase connection strengths between two hidden units or between a visible unit and a hidden unit when they fire together. And the other rule, which you need, go to sleep, generate images, and whenever two units are on together, and generate images by updating the hidden and visible units until you reach thermal equilibrium, those two rules do exactly the right thing in expectation. You have to say in expectation because they're noisy. But on average, they do the right thing. And I'm now going to show you a tiny bit of math, because it is, after all, a physics lecture. And you might have thought at this point, I deliberately kept math out of it, so it was available to the general public. The general public can now stop listening for the next 3 slides. Yes, so what that procedure achieves is it's a maximum likelihood learning procedure. It changes the weights of the model to maximize the likelihood that the model would generate data like the data you saw. Which is what I just said. Oh, sorry, before I give you equations, I just want to say why this learning rule is so surprising. So suppose my data just consists of 2 bits, these 2 visible units at the 2 ends of the chain. And suppose the training data just consists of saying you either get 0, 1, or you get 1, 0. In other words, those 2 bits hate each other. When one's on, the other should be off, and vice versa. But their only communication is via this chain of hidden units. And I want to know how I should change W1 to make the system work better. Well, because the 2 visible units need to turn each other off, then the product of all those weights, W1 times W2 times W3 times W4 times W5, has to be negative. If that product's negative, then they'll inhibit each other. That means to know how to change W1 to make things work better, you have to know the value of W3. Now, if you do something like backpropagation, you find those values by sending signals backwards through the network. But in a Boltzmann machine, how does W1 know W3? Because it needs to know something about W3 in order to know whether it should increase or decrease in order to make the system work better. And the answer is, everything it needs to know about the other weights is conveyed by letting the system settle to thermal equilibrium in these 2 phases. Said all that? Yes, W1 needs to know about W3. I just said that. Now the equation. So if I give you an image, V, a visible vector, and I ask you, how should I change a weight, any of the weights in the system, to make V more probable when the network's just generating data? So when this Boltzmann machine is generating images, how do I make the image V more probable? Or rather, how do I change a particular weight between a neuron I and a neuron J to make this image more probable? And the answer is, you get the exact gradient by looking at the difference between, so this is the derivative of the log probability of a particular training vector under the model with respect to one of the weights in the model. And that is the difference between 2 correlations. The first one is the expected value of the product of the states of 2 neurons, I and J, when you're clamping vectors on the visible units. In this case, This is just for V, it's when you're clamping V on the visible units. And the second term is the expected value of the product of states of two units when the system is running freely, when it's dreaming. But those have to be the expected values at thermal equilibrium. And then you've got the gradient. And so this is a much nicer way to get the gradient than backpropagation. You don't need to send a different kind of signal backwards through the network. You don't need to interrupt the ongoing processing, because what you're going to do is you're going to get one half of the gradient while you're awake and the other half while you're asleep. And then you just change the weight by the difference between the correlations you measure between two units when you're awake and the correlations you measure when you're asleep. And of course, you could remember these correlate. When you're awake, you could remember the correlations from the previous night, and so change the weight by the difference between the current correlation and the correlation you estimated the previous night. And then the question is, why is that derivative so simple? So, the energy of a state of the network is just the product of the two activities times the weight. So if you differentiate with respect to the weight, you just get the product of the two activities. So the derivative of the energy with respect to weight is just the product of two activities. And at thermal equilibrium, the log probability of state is a linear function of the energy. So maybe we'll come to that. Yes. So if you ask, what's the probability when it's generating that it'll generate a visible vector V? Well, that's the top line is the e to the minus the energy for all the possible configurations that include V as a visible vector. So you sum of all the possible hidden configurations. And so that's the probability you'll find V. If you know how to figure out the probability of a complete configuration of the network, just sum over all the ones that have V as a visible vector, and that's the probability it'll generate V. So that's the top line. And then the bottom line is summed over all possible visible vectors. So now you're summing over all possible configurations of the network. It's what physicists call the partition function. And if you think about differentiating that, if you want to increase PV, you want to make the top line bigger, and you want to make the bottom line smaller. And the way you make the top line bigger is by, that's the wake phase, by increasing the strength of connections between two units that are both on, because you settle the thermal equilibrium. So you'll have V with one of the H's that goes with V nicely, and you'll make it go with V even more nicely. And then the negative phase is making that bottom line smaller, which is the way to make V bigger. And that's why you do unlearning in the negative phase. So I think that's it for the equations. You can start listening again. The process of thermal equilibrium essentially gets all the information you need to get the gradient for a weight into the difference of two correlations in this wake and sleep phase. Now, that's all very pretty, but there's some problems with Boltzmann machines. The main problem is they don't work. And that's because settling to thermal equilibrium in a big system takes a very long time. So that was sort of it for Boltzmann machines for 17 years. There's engineering problems. They take a long time to settle. And the learning signal's noisy, but that's a minor problem. It's taking a long time to settle to thermal equilibrium means that this beautiful relationship you get at thermal equilibrium just is too expensive to compute because it takes so long to settle to thermal equilibrium. There's also a problem from the neuroscience point of view. As a theory of the brain, connections between real neurons are not symmetric, and people alternate between wake and sleep at a very coarse time scale, and we don't update neurons one at a time. Actually, as long as you update them randomly, the last thing doesn't matter much. But they're clearly not how the brain's working. So they have two properties. They don't work as engineering, and they're not how the brain's working. And you can get, they've got a third property. You can get a Nobel Prize for them. So 17 years later, I realized that if you make a restricted form of Boltzmann machines, where you only have one layer of hidden units and they don't talk to each other, so that's very restricted. You just have visible units and some hidden units that don't talk to each other. That's why they're restricted. then you can get a very fast learning procedure. So, if you clamp the visible units and the hidden units don't talk to each other, you settle to thermal equilibrium in one step. You just simply visit each hidden unit, and you can do that all at the same time. You update them based on the input they're getting from the visible units, and you're at thermal equilibrium in one step. So that's the wake phase sorted out. That's very efficient now. But what about the sleep phase? You still require alternations between updating the visible units and updating the hidden units, and it looks like that's going to be slow. It's very hard to estimate how slow it's going to be. Mathematically, just very tricky to estimate that. But you can try it, and so I tried it. So to begin with, I would put data on the visible units, I'd update the hidden units, then I'd update the visible units again, call that a reconstruction, because you've taken the information in the visible units, you've activated the hidden units. From the information in the hidden units, you now activate the visible units, and you'll get something like a reconstruction of the image, not perfect. And then you activate the hidden units again. And then you go up and down and up and down and up and down like that for a long time until you reach thermal equilibrium. And then you can learn by taking the correlation between the data and between I when it's data and I on the first step data of the hidden units, and taking the same correlation after you've run this chain for a very long time. And that'll give you the correct gradient. But I was interested in how long do you have to run it for. So I ran it for a certain length of time and the learning worked. And I ran it for less time and the learning worked. I ran it for less time and the learning worked. And in the end, I just went up and down and up again, and the learning still worked. So that's really good, because now all this business is happening, thermal equilibrium has gone away. We just go up and down and up again. And I'd made a very naive logical error, which is, if you reach thermal equilibrium, the learning will work. But that doesn't imply that if the learning works, you reach thermal equilibrium. The learning can work for other reasons. And so there's this algorithm called contrastive divergence, where you just go up and down and up again. And where it says 1 on the connection between I and J, you measure the correlation. How often are they on together? And where it says 2, you measure the correlation, and you just subtract one correlation from the other, and the thing learns pretty well. It's very hard to prove mathematically it's doing the right thing, because it isn't. But it works pretty well in practice. And so then we could make these simple stripped-down Boltzmann machines, restricted Boltzmann machines, actually practical. And they were actually used by Netflix for predicting which movies you'd like. There was a competition where they offered $1 million if you could do 10% better than Netflix at predicting which movies people would like. And the competition was won by a team that used our restricted Boltzmann machines and another method called matrix factorization and combined them, and that won the competition. So RBMs were actually useful for something finally, but only this restricted version. So maybe Boltzmann machines are a little bit useful. But the restricted version has thrown away most of the power because the hidden units can't talk to each other. Okay, so now you can do something. You can say, maybe I can have multiple layers of these. And I can learn a hierarchy of feature detectors. And so the idea is that you train an RBM, you show it data, and you have hidden units, and you train the weights between the data and the hidden units. So the hidden units now are capturing features of the data, like combinations of pixels that occur quite often, or combinations of lines that occur quite often. Once you've learned that RBM, you then take these hidden units, these hidden neurons, and take their binary states and pretend that's an image, and just do it again. So you copy those states and just learn a second RBM. And then you take the hidden states of that RBM and copy them again and learn a third RBM. And there's a very nice variational bound which shows that if you do this just right, you can guarantee that as you learn more and more of these Boltzmann machines, you can stack them up and make one big model out of them, and each time you add another Boltzmann machine, your model gets better. Or rather, the variational bound on how good your model is improves. Your model might get worse, but the variational bound improves. But I'm not going to go into that. But it does justify doing this. So now we can take all those restricted Boltzmann machines that we learned efficiently, and we can stack them up like that. And then we've got weights for a multi-layer network that looks at images and extracts features and features of features and features of features of features. And then we can just put class labels on top. We don't know the weights to the class labels. Those red things, we don't know the weights. But we've already got all the features. So we've got the features for a multi-layer net. And it turned out that that was a very good way of initializing deep neural networks that you're going to train to do things like object classification or speech classification. And so finally, there's this very, very tenuous link that says a stripped-down version of Boltzmann machines, if you stack them up, is a good way to initialize backpropagation. So there is actually a link, and you can think of it as like an enzyme. For about 4 or 5 years, people initialized neural nets this way and got them to work much better, significantly better, particularly for speech recognition. Then they discovered other ways of initializing nets, and they threw away the Boltzmann machines, and that was the end of Boltzmann machines. So think of them as an enzyme. They were a technique that helped deep learning be born by initializing the nets well. So there is a very tenuous link between Boltzmann machines and current neural nets, but it's tenuous. So just to summarize, they were like an enzyme. They helped us make the transition to current neural nets. Now, I still think the idea of using unlearning during sleep may be something really useful for understanding how the brain works. There is one very interesting property of people, which is if you deprive them of sleep, they go completely crazy. If you just deprive people of sleep for a week, they go completely psychotic, and some of them never recover. And most theories of sleep don't explain why that is. But if sleep is for unlearning, that does explain why it is. If you just use a positive Hebb-type rule, and you don't do this unlearning, then the whole system will go crazy. That's the end.
Well, Jeff, thanks so much. I'd like to thank Dr. Hinton for this wonderful presentation, from which we've all learned much more about how an idealized physical setup or system can shed light into some aspects of how our brains actually work. But now I'm confused. I don't know how much we've learned about how our brains actually work. We've really learned a lot of great questions. So to keep the conversation going, I'd like to take the opportunity to introduce Dr. Yoni Khan, who's standing next to Dr. Hinton. He's our newest professor in the Department of Physics, and he holds a concurrent faculty affiliate status as well with the Vector Institute. Yoni was formerly an assistant professor in the Department of Physics at the University of Illinois at Urbana-Champaign. He's interested in designing the next generation of direct detection experiments for dark matter and dark sectors using molecular and condensed matter systems. He also studies the theory of machine learning and applications to high-energy physics and astronomy, and has a strong interest as well in physics education. He's actually published a textbook preparing students for the physics GRE, the graduate exam. It's called Conquering the Physics GRE, Cambridge University Press. So Yoni and Jeff, we're very much looking forward to your conversation, and after which we'll take a few questions as we have time for. So come on up for the fireside chat, and
Okay. This is where it becomes clear that I don't actually know any physics.
Well, I hope to convince you to the contrary. So thanks so much for a really wonderful talk that, I had a list of questions that I was thinking of asking you, and then I'm kind of tempted to just throw them all out and just go off what you said, because it was, I think, really interesting. But let me start with, one thing that you mentioned over and over is this idea of correlations and correlation functions being useful for either the learning procedure or for understanding what's happening. In most areas of physics, correlation functions are how we describe the universe. Even, the particle collisions that will go on at the Large Hadron Collider, you can think of them as correlation functions, these things called quantum fields, or, what Professor Kushner studies with, climate science. If you have a time series of data and it's random, kind of, some of the information you can get out of it is, how much is weather at this time correlated with weather at that time. And I'm wondering, we have these enormous trillion parameter models now. There's lots of numbers inside those things. Can we use any of this intuition for kind of physics-inspired correlation functions to tease out any of the the meaning or interpretability of what's happening inside those large networks?
Probably, but I don't know how to do it. That is, many people say we're never going to be able to trust these big neural networks until we understand how they're working. I think we may well never understand in detail how these big models are working. I mean, we programmed them, so we know roughly the architecture of the net, but how they work depends on what they learn from data. And when something with 1 trillion real value parameters makes a decision, it may be that there is no simpler explanation of why it did that than the values of those 1 trillion parameters. Now, I should say, most people in the field think we can do better than that, but I'm not convinced we can do much better.
So let me also ask, you mentioned this idea of the restricted Boltzmann machine is like an enzyme that catalyzed some advancement in deep learning. And my understanding is there have been several of those physics-inspired advances that have managed to do something pretty amazing. And I think one example is this idea of scaling laws, that as you increase the size of a network or you give it more and more computing time, it does better and better, but it does better and better in a particular way that physicists would call a power law, and that if you make a certain kind of plot, it looks like a straight line. And my understanding is that idea was inspired by that kind of behavior showing up all the time in physical systems, in condensed matter systems, in high energy systems. And the fact that this has happened, there are other examples, several times suggest to me this is not an accident. So,
well, physicists have thought a lot about things, right? And they're very smart. So, like, a lot of mathematics came from people thinking about physics.
True.
I think probably some of Newton's mathematics came from trying to figure out why the moon didn't fall into the earth and things like that.
Right, right.
So it's not surprising that physicists are among the first people to come across fancy mathematical techniques.
Well, let me ask, where do you think the physics perspective can be most useful in understanding deep learning, and maybe to contrast it with the perspective of, say, psychology or biology or traditional computer science?
I wish I could answer that. So Ganguly at Stanford is an ex-physicist and has done very nice work on showing what's happening in the weights as models learn. So, I mean, my belief is insights from physicists are going to be useful, but let me be a politician and just change the subject slightly and tell you a piece of physics that really is very useful. So people in machine learning use variational methods, which come from physics. And I want to try and describe for the general public how you might use a variational method, or how you get an insight from a variational method, to understand how you could get efficient communication between models. So let's suppose you have two different ways of encoding exactly the same event. And you want to communicate this. We have a sender and we have a receiver. And the sender wants to communicate this event to the receiver using as few bits as possible, sending as few bits across the channel as possible. And so let's suppose you want to tell someone it's raining. And being Canadian, you can say, it's raining, or il pluie. I don't speak French, but I think that's right. I'm not a real Canadian. So a normal person would say, well, if it takes sort of 10 bits to say it's raining, it takes 10 bits to say il pluie, what you should do is just pick one and do it, and it's going to take you 10 bits. But a physicist would say, okay, you've got two different ways of coding the same thing. What if we stochastically picked one of those ways? So we flip a coin, and we pick one way. Now, it looks like you don't win anything by doing that, because you flipped your coin, and you either say il pluie or you say it's raining, and you still have to send 10 bits. But suppose that instead of flipping a coin, what we do is we run a little random number generator to get our random bit. And suppose that the receiver has the same random number generator. So now, we're going to run the random number generator and decide whether to say it's raining or il pluie. The receiver can also run that random number generator and see which random bit we used. And so actually we can communicate the random bit that we use for picking between these two codes. And so the receiver can actually get 11 bits of information. He can get the 10 bits of information that tell him whether it's raining or not, and he can get another bit of information, which might just be about a random number generator. But instead of using a random number generator, we could have just taken some other message we wanted to communicate. Suppose you're doing consulting on the side and you want to do something else at the same time. You can communicate this other message one bit at a time by your choice between whether you say il pluie or it's raining. And so it turns out that a stochastic choice is actually the right thing to do. And if you look at a free energy function, then the number of bits it takes to send the code is like the energy, and the probabilities you assign to codes are like the entropy. And the best thing to do is use a Boltzmann distribution. So if you've got a code that's a bit longer than another code, you use that less often, but you do occasionally use it. And so what happens is results from statistical physics show up in coding theory like this if you've got alternative codes. It's actually better to use the code stochastically than to just pick the cheapest one. That's a little bit of physics showing up in.
Which is, it's really, it's a nice example of, the kind of the confluence of fields. The work that Shanna did on entropy has now found its way all into quantum information and the way that people think about information in physical systems. I want to riff a little bit on the subject of cooperation and message passing. So physics has this very long tradition of enormous worldwide collaborative projects, of which CERN, the European Organization for Nuclear Research, is one of them. The history is really amazing, kind of founded to induce cooperation after World War II, but managed to do amazing things like discover the Higgs boson, which won the Nobel Prize a couple years ago. And by putting a lot of very, very smart people on a similar task, was able to make amazing progress. It feels like we might need something like a CERN for AI nowadays. What would such a thing look like? How would people contribute to it? How might it be organized, and what would it do?
Given the current political situation, it would clearly be in Europe. There's a big problem with that. So right now, people are organizing a petition to say we should have a CERN for AI. And I'm trying to decide whether I want to sign on to that. The main problem is AI is going to be useful for lethal autonomous weapons. And all the countries that sell arms, like the US and Russia and China and Israel and Britain, are all going to want to develop their own lethal autonomous weapons. And they're not going to want to collaborate. It's also good for cryptographic attacks and things like that. Cyber attacks. So I think there's a lot of reasons why it's going to be much harder to get countries to collaborate. Like, imagine you tried to set up CERN at a point where people thought, okay, we've got the atom bomb, we've got the H bomb, and then there's some other kind of bomb we haven't quite got yet. Let's all collaborate to explore it. It wouldn't have worked like that, right? They had to have believed that, we got the H bomb now, and doing this high energy physics probably isn't going to give us anything worse than that, so we can collaborate. I think it would be a very good idea if we can make it happen, but I think there's going to be a lot of political reasons why governments don't want to do it.
So maybe let me just ask one more question, and then we'll get to some questions from the audience. The analogies between deep learning and big world-changing weapons like nuclear bombs, there's a lot of really interesting resonances there. And I think one of them is the fact that the underlying physics that governs how atom bombs work is stuff that I teach in my graduate particle physics classes, because it is part of how the world is described at a fundamental level. But of course, if you take that with a quantity of some material that you can dig up somewhere, it makes something that is unimaginably destructive. And I wonder how you think we should be balancing these desires for understanding this tool that is AI is going to do amazing things for good, certainly in addition to all the things that it could do to make the world worse. But how do we balance the understanding with the need for safety?
Okay, so there's one thing I think quite strongly, which is you wouldn't make it so you could buy on the web fissile material. Because with nuclear weapons, the difficult bit is getting the fissile material. I mean, it's all difficult, but that's the most difficult bit. That's very expensive. And if you want to stop people having them, you bomb the facilities that make the fissile material. So you'd be crazy to release the fissile material. So because maybe researchers say, well, I'd like some fissile material, so I can play with bombs. Oh, well, we should give them. It's unfair not to give it to researchers in universities when countries have it. But it'd be crazy. And Meta started it, but they now release the weights of these large foundation models. And the point is, the main constraint on what you can do with AI is that it takes a lot of money and a lot of data to train a large foundation model. Once you've got the weights of the model, you can then use that model for doing all sorts of other things with not much training. So I think they were completely crazy to make the weights public. People talked about it like it was open sourcing, but it's not like open sourcing at all. In open sourcing, you release code, and people look at that code and say, wait a minute, that line is a bit suspicious. When you open source weights, they don't look at it and say, oh, look, this weight's a bit suspicious. They just take those weights and they train them to do something else. But they're starting from a very good starting point. So that boat has sailed already. It was crazy to release the weights of these big models, because that means any cyber criminal who can get his hands on a few $100,000 can retrain one of them. Sorry, that's bad news, right?
Well, given that this stuff is already out there in the world, do you think there are things that we can learn from it that will help us prevent some catastrophe that will come from the larger models that are trained after it?
I'm quite pessimistic. So my friend Yann LeCun, who works for Meta, is very optimistic. And it turns out your personality has a big effect on what you predict the future is going to be like. And it turns out I'm right. So psychological research shows that if you take normal, healthy people, normal, cheerful, healthy Americans, and you ask them to predict what's the chance that in the next 5 years you or a member of your immediate family will be seriously injured in a car accident. I don't know the actual, I can't remember the numbers, but they'll say things like 1%, and actually it's like 10%. And you ask them, what's the chance that you or a member of your immediate family will get cancer in the next 5 years? And again, they're much too low. They just underestimate the probability of these awful things happening. If you take paranoid schizophrenics, they overestimate. If you take mildly depressed people, they get it just right.
So maybe we have, it would be great to continue the conversation with some questions for the audience. So yeah, why don't you go ahead and, yeah.
Let's thank both of them for a really nice conversation. I don't know if we have a mic runner or not. If not, oh, we do. Okay, so questions from the audience. And I see a hand raised in the back there.
So, Dr. Hinton, wonderful talk, not only for the experts, but also for the general public. And would like to ask you specifically, my name is Azim Rizvi. There is a book also coming over recently, Genesis. Mr. Kissinger was also one of the authors, and then other founders of...
When you put your hand like that, you put the mic the other way, and I can't hear what you're saying.
And there's a mention of an ethos-based future development of AI, where they talk about the human ethos being built as part of the whole regulatory framework, and an understanding that you alluded to globally, a cooperation that need to be in place before we pursue the artificial intelligence to get to a point where the AGI is achieved or we go beyond that? We'd like to kind of know about, like, once there is a new tech comes, there's always this debate about regulation and when that regulation is required and when it's too early about it and or we too late already for the artificial intelligence. Your answer to that will be appreciated.
Okay, so the first point is we're not going to be able to slow it down because it's got too many very good uses. I mean, more or less all industries can make use of AI. It's going to be very useful in healthcare. It's going to be very useful in education. It's going to be very useful in designing new materials, which may be very helpful for things like climate change. So we're not going to be able to slow it down. The question is, are we going to be able to develop it safely? And there seems to be not much political will to do that. People are willing to talk about things like discrimination and bias, which are things they understand. But most people still haven't understood that these things really do understand what they're saying. We're producing these alien intelligences. For now, we're in control, but we're making them into agents so they get to do things in the world. And they're very soon going to realize that a good thing to do to achieve your goals is to get more control. And so I'm very worried that we're in a situation now where we'd like really strong, sensible governments with intelligent, thoughtful people running them. And that's not what we've got.
There's a question. Yes. Okay, yes. Go ahead. Yeah.
Hi, Jeff. How are you? My question is about power laws. And so there's been this theory or idea that as we scale more compute and more data, we're going to have more performance models. I think Sam Altman mentioned that it's correlated with the log of the compute and the data. But ever since the release of GPT-4, we've seen that every single update of LLMs has been underwhelming to a bit. Like, we haven't seen the big jump that we saw from maybe GPT 3.5 to GPT 4. And most recently with the Grok 3 release, there was a lot of hype about the amount of compute that went into it with Elon Musk and XAI. But it was also not like that great model. I'm wondering if you think that we've sort of plateaued with regards to compute and data, and that we need a different approach. And that's it.
Yeah,
Thanks.
I think it's quite reasonable to think we're getting diminishing returns from this scaling. And basically, you get a little bit better each time you double the amount of compute. That's the log, right? So it's getting more and more expensive to get these small improvements. However, scaling has taken us a long way. We've got things that are really pretty smart now. And new ideas are also going to take us further. And new engineering tricks for making these more efficient are going to take us further. So I'd be very surprised if it just plateaus. People have been predicting for ages that it's about to just plateau, and it hasn't. But it may be that we need more good ideas to make it keep developing. So if you look at Moore's law, for example, Moore's law, for as long as I've been alive, almost as long as I've been alive, and people have been saying Moore's law is about to come to an end. And computers just got faster and faster and faster as they made them smaller and smaller and smaller. And then it got to the point where they were doing like a gigaflop, and people said, they're not going to get any faster, it's the end of Moore's law. And then they went off at right angles and started getting more and more parallel. And we got NVIDIA GPUs and things. And Moore's law just kept on, in fact, even accelerated. So I think it's going to be like that. I think scaling took us so far. And scaling is maybe like making computers faster and faster. But now making computers more and more parallel kept Moore's law going for another 10 years or so, maybe more. And I think we're going to get new ideas that are going to make things work better. There's now so many smart people working on this that I can't believe there aren't good new ideas that are going to make it work better.
Maybe one last question. Could we actually, okay, we'll have maybe in the back and then a final one to the front. Yes.
Hi. So the theory of active inference has sensory neurons running parallel to motor neurons, and they're tightly coupled, and the error signal in the sensory neurons activates a motor neuron to make some kind of correction, which is, I mean, that's about activations and not weights, but I'm wondering, is there something like backpropagation possible here? Like if you have these actual parallel sets of neurons running, is there something like that?
Yes, you can actually make a version of backpropagation work in a brain. It just doesn't work as well as it does in a digital computer. And the cerebellum is one place where people have thought there may well be something like backpropagation. Because you get this visual slip, you get a visual slip signal that can be used to train your vestibular apparatus, which is much faster. And so you can use visual slip to train vestibular. And that's where you get the error signal for backpropagation. And people have speculated about whether something like backpropagation goes on there. But you can also do backpropagation in a brain by using temporal differences. So backpropagation initially seems very implausible because in the forward pass, you're sending neural activations. And in the backward pass, you're sending neural sensitivities. The signal that's coming back is how sensitive is the error to a change in this neuron, a derivative. So that's a completely different kind of information. But you can use temporal derivatives to stand in for error derivatives. So you can have a system that does two passes, and the difference between the activation in those two passes is your error derivative. And there's some evidence the brain might be using temporal derivatives as error derivatives. So for example, you have neurons that detect motion. You have neurons that detect location. And then if you ask, well, how do you detect motion? The obvious way to do it is to look at the difference in location over time. But that's not how you do it at all. You have separate neurons that represent motion. So why can't you use the difference of location neurons to represent motion? And one possible answer is because you're using those temporal differences to represent error derivatives. So there's a whole paper by me and Joshua Benja and other people. Actually, I don't think Joshua was an author of that. There's a paper by me and various people on using temporal differences as error derivatives and showing how you can implement a version of backpropagation in a brain. But the point is it doesn't work very well when you're trying to pack a lot of information into a few connections. It won't get information into bottlenecks. If you have big, generous neural networks with plenty of spare capacity, these techniques will work and will allow you to do something like backpropagation, but not as efficiently as in a digital computer. So it may be that the brain has ways of doing stuff like backpropagation by using temporal differences, but nobody really knows. And it's been somewhat disappointing, the attempts to understand what the brain's up to in perceptual learning. I don't think we got there yet.
So, final question from the Martin family, which is a fitting end.
Thank you so much for the fantastic lecture. It was incredibly interesting. I have so many questions, it's hard to choose one, but we were just looking at image generation, not image recognition, and I was wondering if there is some sort of relationship between the wake state and the sleep state. Like, is image generation where the trained system in the wake state is generating the image based off of what it's learned?
So I should emphasize that Boltzmann machines were a nice idea about how you get a learning signal that used simple relationships that you get at thermal equilibrium in statistical physics. But I don't think they're what's actually going on, unfortunately. And they're not particularly good engineering. So I think it may well be that something like sleep for unlearning is going on, but not the Boltzmann machine.
All right. Well, we've come to the end of the evening, so I really would love to thank Dr. Hinton again and Dr. Khan for a wonderful fireside chat, and of course for the amazing lecture we heard in the first hour. So let's thank them again.